Welcome to the Explainer. Listen, if you've spent any time at all wrangling data, you already know the landscape moves incredibly fast. But today, we're locking in on the absolute powerhouse of modern structured data. We're talking about gradient boosting. We are going to completely demystify the complex math behind the three specific engines that literally run the modern predictive world. So here is the big question to kick things off. Why do three specific frameworks completely dominate modern machine learning? I mean, out of all the algorithms ever invented, why have XGBoost, LightGBM, and CatBoost become the undeniable go-to industry standards for everything from banking algorithms to winning global data science competitions? Okay, let's dive into this. Here's our roadmap. First, we'll look at the gradient boosting foundation, then XGBoost, the regularized pioneer, followed by LightGBM, the speed demon, and CatBoost, the categorical master. After that, we'll do the ultimate algorithm showdown, and finally, real-world action, focusing on credit risk. Section 1, the gradient boosting foundation. Before we start comparing the heavyweights, how exactly do these algorithms convert weak learners, models that are barely better than a random guess, into an unstoppable, strong learner? Well, the secret lies in something called pseudo-residuals. Think of this like playing a game of golf. Your very first swing gets you closer to the hole, but obviously you aren't there yet. That remaining distance? That's your residual. In gradient boosting, we build decision trees sequentially. The early trees take massive swings at the biggest errors, which effectively reduces our model's bias. Then the later trees step up and basically tap it in, fine-tuning that remaining distance to reduce the variance. Every single new tree is mathematically trained to correct the precise mistakes of the trees that came right before it. Section 2, XGBoost, the regularized pioneer. Now, that foundational idea of boosting was brilliant, but it had a flaw. It tended to overfit the data. XGBoost arrived on the scene as a total pioneer by integrating regularization directly into its math. Older boosting methods used first-order gradient descent. That basically calculates a simple slope to slowly inch toward the lowest error. XGBoost completely flipped the script by using the second-order Newton-Raphson method. So what does that actually mean for us? Well, by calculating the Hessian, which is the second derivative, XGBoost looks much deeper into the actual curvature of the loss function. It takes a much faster, smarter leap toward the optimal tree, scaling its steps automatically. But how does it handle millions of rows without just, completely crashing your machine? This is where XGBoost introduced the approximate greedy algorithm. Instead of painstakingly evaluating every single data point to figure out exactly where to make a spit, it quantizes feature values into percentile buckets. It only checks the boundaries of these buckets. This massively scales up its ability to find splits without getting completely bogged down in endless computations. Section 3, LightGBM, the speed demon. Microsoft saw the memory and computational bottlenecks that were actually still present in standard boosting, and they completely redesigned how trees grow. Now, what's really interesting here is the shift from level-wise to leaf-wise growth. Traditional trees grow level-wise, right? Like a perfectly balanced pyramid, expanding all the nodes at the same depth all at once. LightGBM throws that out the window. Instead, it greedily hunts down the single leaf anywhere in the entire tree that promises the absolute maximum loss reduction, and it splits just that one leaf. The result? An asymmetric tree that hits equivalent accuracy using roughly 30 to 50% fewer trees. Add that leaf-wise growth to the concept of feature binning, also known as histogram-based learning. Instead of tracking exact, precise decimal numbers for every single data point, LightGBM basically lumps continuous features into about 256 discrete bins. Gradients are then calculated per bin, not per sample. Together with a really clever technique that bundles mutually exclusive features, this creates a radical 5 to 10 times speed up while barely touching the accuracy. It's just wildly efficient. Section 4, CatBoost, the categorical master. Developed by Yandex, CatBoost was specifically engineered to rescue data scientists from the massive headaches and heavy bias of one-hot encoding text categories. But to really appreciate how, we have to define a core weakness of traditional boosting: target leakage. This happens when the model computes gradients using the target values of the exact observations it's currently evaluating. Essentially, the model accidentally peaks at the answer key. This causes it to know way too much and silently overfit to your training data. CatBoost ingeniously defeats this target leakage with something called ordered boosting. It's a really elegant three-step solution. First, it randomly permutes or shuffles your dataset. Then, when it computes split statistics for a specific row, it intentionally restricts the flow of information so the model can only look at rows that appeared earlier in the shuffle. This stops leakage dead in its tracks. Combine this with its use of deeply balanced, interpretable oblivious trees, and you get incredibly pure, unbiased estimates. Let's move to and see how this builds. Section 5, the ultimate algorithm showdown. So we have these three mathematical giants. Let's put them in the ring together and rapidly run through these benchmarks on a million rows of data. For pure speed and memory efficiency, LightGBM is the undisputed champion. It processes that million-row dataset in roughly 2 to 3 minutes with remarkably low memory usage. XGBoost sits right in the middle at around 10 minutes, while CatBoost takes a bit longer, up to maybe 15 or 20 minutes. And that's because of the heavy bookkeeping required for that ordered boosting we just talked about. But let's flip the perspective for a second and look at performance quality out of the box. Here, CatBoost is absolute king. While XGBoost and LightGBM actually require you to manually encode categorical strings into numbers, CatBoost natively absorbs them using highly sophisticated target encoding. Because of those symmetric trees, the tuning effort is incredibly low, and its out-of-the-box accuracy is widely considered the best of the three. Section 6, Real-World Action, Credit Risk. Let's bring all this dense theory firmly into reality. Imagine you are a practitioner tasked with predicting who will default on a loan. Predicting those defaults is incredibly complex because the relationships are highly nonlinear. Simple, traditional models like logistic regression top out around a 0.77 AUC score on standard datasets. Random forests do better, hitting maybe 0.84. But our tree boosting methods effortlessly capture those hidden, complex interaction effects in the data, reliably hitting an impressive 0.88 and beyond. So the crucial point is that massive jump right there. You're getting 10 to 15% better performance than baseline traditional models. In institutional risk modeling, that percentage translates directly into literally millions of dollars saved by confidently avoiding bad loans and accurately approving the good ones. If you're ready to actually deploy these models, here is your pragmatic, ready-to-use checklist for tuning them. Always start by dialing in your learning rate between 0.01 and 0.1, and absolutely pair it with early stopping to halt the training before it just memorizes the noise. Control the complexity of your trees through max depth or leaf limits. Make sure to use row and column subsampling, meaning you randomly hide pieces of data from each tree to force them to learn robust patterns. And finally, pick your framework purposefully. LightGBM for pure speed, CatBoost for dense categorical data, and XGBoost for total custom control. We've seen how these frameworks master the math of learning. They minimize errors, dodge computational bottlenecks, and protect against data leakage to give us unprecedented predictive power. As these algorithms push the mathematical limits of predictive accuracy, what invisible patterns in your own data are still waiting to be uncovered? I really hope this explainer has given you the clarity to go out and find them. Thanks for watching and keep learning.